My feet are numb. Just keep moving. How much longer do we have out here? Target bearing 040. Confirmed. Loader, feed the belt now. Up and ready, gunner.
January 1941. A bitter wind cut across the concrete expanse of an Army proving ground on the outskirts of Philadelphia. Snow clung to the edges of steel platforms, and the smell of machine oil mingled with the crisp, metallic tang of cold air. Soldiers in heavy wool coats huddled around emplacements, their breath fogging in the icy air, eyes scanning the gray horizon where no enemy aircraft appeared. Yet, inside a nearby factory, the rhythmic hammering of presses and the hiss of steam echoed through cavernous halls. Engineers hunched over .50 caliber Browning machine guns, examining every barrel, every gear, as if the fate of a nation depended on the perfect fit of each part. On paper, these were infantry weapons, not anti-aircraft guns. On paper, America had almost nothing to defend its skies. The tension was palpable. Across the Atlantic, German bombers roared over France, flattening cities with terrifying efficiency. Here, in quiet workshops and empty training fields, a single question hung in the air. Could these familiar rifles and machine guns be transformed into a shield for a nation unprepared for modern aerial warfare? Every clink of metal hinted at a looming reckoning. By January 1941, the world had already been engulfed in war for more than a year. In Europe, the German blitzkrieg had rewritten the rules of modern warfare. Poland had fallen in 1939 within weeks. France, Belgium, and the Netherlands had crumbled under the relentless combination of fast-moving tanks and concentrated aerial bombardments. The Luftwaffe, Germany's air force, dominated the skies, turning cities into ash and terrorizing entire populations. Britain clung to survival. Its navy and remaining air force stretched thin, desperately improvising defenses as nightly raids pounded London. The scale and speed of these attacks revealed a grim reality. Air power had become a decisive force, capable of destroying not just armies, but entire nations' infrastructure. Across the Atlantic, the United States watched from a distance. The nation remained officially neutral, its military doctrine still rooted in the experiences of World War I. American planners focused largely on infantry, cavalry, and coastal defenses, assuming any aerial threat could be managed with rudimentary observation posts and limited machine guns. Anti-aircraft artillery was sparse, scattered, and largely outdated. The U.S. Army had a handful of dedicated 3-inch AA guns, most dating from the 1920s, with minimal range and poor fire control. These weapons were sufficient for training exercises, but utterly inadequate against the high-speed, low-altitude attacks now standard in modern combat. Industrial capacity existed, but it was underutilized for wartime purposes. Factories like the ones run by John Browning's successors had produced thousands of reliable infantry weapons for decades, but not a single machine gun had been designed specifically for anti-aircraft defense in the United States. Bureaucracy slowed innovation, and many military leaders remained skeptical of the need for rapid adaptation. Some argued that America's oceans provided natural protection. Others warned that without modern AA guns, cities, ports, and naval installations would be sitting targets. Meanwhile, intelligence reports painted a worrying picture. German Luftwaffe bombers were equipped with dive-bombing capabilities and increasingly sophisticated navigation systems. Japanese air units in the Pacific were conducting reconnaissance and small-scale attacks, testing defenses across Hawaii and the Philippines. Any American response would require weapons that could fire at angles far beyond traditional infantry use. Guns capable of tracking aircraft moving faster than the human eye could easily follow. Faced with these challenges, the U.S. Army began reviewing its existing inventory. The .50 caliber M2 Browning machine gun and the .30 caliber M1919 were reliable, battle-tested, and plentiful. They had proven their worth in World War I, in infantry roles, on vehicles, and as mounted weapons for border patrols. But these guns had never been intended to reach aircraft cruising hundreds of feet overhead. Elevation mechanisms were limited. Traversing a gun quickly enough to track a plane required new mounts, new sighting systems, and ingenuity. Yet, time was running out. The Atlantic and Pacific theaters were becoming active zones, and any delay could prove catastrophic. Within factories, engineers and machinists began examining these weapons in detail. Barrels were reinforced, triggers adjusted, and cooling systems rethought to sustain the rapid, prolonged fire necessary to hit fast-moving aerial targets. Every calculation mattered. The rate of fire, bullet trajectory, and even recoil patterns could determine whether a weapon could destroy a bomber or merely waste ammunition. In meetings, Army officers debated mounting configurations, tripods, pedestal mounts, even adapting naval-style carriages, while engineers sketched prototypes on chalkboards and in notebooks. At the same time, political tension mounted. The U.S. government was still officially neutral, but President Franklin D. Roosevelt had begun to prepare the nation for possible involvement. Lend-Lease legislation had already started supplying Britain and its allies with equipment, highlighting America's industrial might. Yet, domestically, isolationist sentiment was strong. Some Congress members questioned the expense of anti-aircraft production, arguing that investing in defensive weapons for a war America was not yet fighting would waste resources better spent on infrastructure or traditional army readiness. And so, a paradox emerged. The United States had the industrial skill, the weapons, and the intellect to build an effective air defense, but it lacked the doctrine, the political mandate, and the modern hardware to implement it. Across quiet proving grounds and echoing factory floors, soldiers and engineers worked against a looming deadline. Each modification of a Browning machine gun brought the country one step closer to a feasible anti-aircraft solution, even as the world burned just beyond its shores. The stage was set. The need for innovation was urgent. The tools were familiar. The challenge was unprecedented. The U.S. Army's existing arsenal was extensive, but it was designed for a different type of warfare. Infantry units carried M1917 and M1919 machine guns, reliable and proven, yet intended to sweep trenches and fields, not skies. The .50 caliber M2 Browning had more potential. Heavy, powerful, and capable of sustained fire, it could theoretically reach low-flying aircraft. But theory and practice were two very different things. Firing at a target moving hundreds of feet above the ground require modifications to both the gun and its mounting. Standard tripods were insufficient. The recoil from rapid .50 caliber fire made precision tracking nearly impossible. New mechanical solutions were needed to elevate and stabilize these weapons at steep angles, while maintaining accurate fire control. Prototype development began quietly. Engineers at Browning factories and testing ranges experimented with adjustable mounts, adding elevation gears, counterweights, and swivel systems to allow rapid horizontal and vertical movement. Some prototypes incorporated rudimentary lead computing sites, designed to estimate the trajectory of aircraft moving at hundreds of miles per hour. Even the ammunition underwent scrutiny. Tracer rounds were introduced to help gunners follow aerial targets in flight. Each adjustment required careful measurement and repeated testing to ensure reliability under combat conditions. The goal was simple in words, but complex in execution. Transform an infantry weapon into a credible anti-aircraft gun without building a completely new system from scratch. Bureaucratic hurdles slowed progress. The Army's Ordnance Department required extensive testing and documentation before any weapon could be approved for mass production. Engineers often found themselves navigating a maze of regulations, memos, and approvals, all while the geopolitical situation became increasingly urgent. Time, however, was a luxury they did not have. Reports from overseas indicated that Germany's air raids on Britain had become devastatingly effective, and Japanese reconnaissance flights over the Pacific were probing weaknesses in American installations. Delay meant vulnerability. Despite the challenges, incremental successes emerged. Early tests demonstrated that with proper mounts and modifications, the M2 Browning could sustain rapid fire at high angles without catastrophic overheating. Adjustments to recoil springs and barrel cooling systems allowed gunners to maintain accurate bursts for longer periods. Field trials at coastal forts and inland proving grounds confirmed that these improvised anti-aircraft weapons could engage low-flying bombers with surprising effectiveness. While far from perfect, the adaptations represented a critical stopgap in America's unprepared air defense network. The human element played a pivotal role. Factory workers labored under long hours, assembling, adjusting, and recalibrating each weapon. Engineers meticulously documented each change, often testing multiple configurations before settling on a solution. Officers conducting trials provided feedback, noting how gunners could physically manipulate the mounts and sights during simulated attacks. This collaboration between industrial expertise and military experience laid the foundation for the first practical U.S. anti-aircraft machine guns. At the same time, leadership debates continued. Some military commanders argued for investing in entirely new anti-aircraft artillery, while others saw adaptation of existing infantry weapons as the fastest route to readiness. The urgency of the Pacific and Atlantic threats made compromise necessary. Money, manpower, and materials had to be allocated carefully, with the understanding that every delay could cost lives once hostilities reached American shores. By mid-1941, the Army had a series of functional prototypes. These included M2 Brownings mounted on high-angle pedestals, with improved traverse mechanisms, reinforced barrels, and enhanced sighting systems. Infantry caliber M1919 guns were similarly modified for secondary anti-aircraft roles. The improvised nature of these weapons was clear. They were not purpose-built, but necessity had forged them into a credible stopgap. Reports noted their potential to defend key coastal installations, factories, and training bases. Yet even as these prototypes moved toward production, the larger strategic picture remained uncertain. Isolationist sentiment at home limited funding, while overseas combat continued to evolve at a pace faster than most American planners could anticipate. The experiments of 1941 would not only determine immediate defense readiness, they would shape American anti-aircraft doctrine for years to come. The stage was set for multiple perspectives to emerge. Human ingenuity, tactical necessity, technological adaptation, leadership decisions, and enemy threats would all converge on a single pivotal question. Could America turn familiar infantry weapons into an effective shield against the deadly skies of modern warfare? Behind every improvised anti-aircraft gun stood countless hands, eyes, and minds working in near-perfect coordination. Engineers and machinists at Browning factories were tasked with a challenge unprecedented in scale. Take weapons designed for infantry trenches and make them capable of tracking and destroying fast-moving aircraft. Each bolt, gear, and barrel had to be carefully examined and recalibrated. Factory workers labored in long shifts, their fingers numb from winter cold, the scent of gun oil mingling with the hiss of steam from hydraulic presses. Mistakes could be catastrophic. A misaligned mount or poorly adjusted recoil system would render the weapon ineffective, or worse, dangerous to the gunner. Yet morale was high. There was a palpable sense of purpose. Every modification was not merely technical, but patriotic. In letters home, some engineers described the work as preparing to protect a country that doesn't yet feel under threat, a quiet tension that underscored the human cost of preparation. The technical challenge of adapting a Browning machine gun for anti-aircraft use was immense. Standard M2 Brownings were designed to fire horizontally at a predictable, static target. To engage aircraft, the guns needed high-angle elevation, rapid traverse, and sustained fire capability. Recoil systems were reinforced to prevent guns from snapping off mounts under repeated high-angle fire. Cooling mechanisms were improved to prevent barrels from overheating during bursts. Even ammunition was reconsidered. Tracer rounds were integrated to allow gunners to visually track bullets against the sky. Prototype mounts, some improvised from modified naval carriages, were tested extensively. Engineers calculated angles, bullet trajectories, and firing rates down to precise tolerances, often creating multiple iterations before settling on workable solutions. The resulting weapons were imperfect, but functionally capable of engaging low and medium-altitude aircraft, a technological leap achieved through adaptation rather than invention. From a tactical standpoint, these adapted guns filled a critical gap in U.S. defenses. Prior to 1941, American strategy assumed air attacks would be limited and predictable. Infantry units were not trained to counter high-speed aircraft, and coastal forts relied on outdated fixed AA guns. The improvised Browning mounts allowed for mobile, flexible anti-aircraft coverage. They could be deployed quickly to protect ports, factories, and training fields, providing a stopgap until purpose-built AA systems could arrive. Gunners learned to coordinate in teams, with spotters calculating lead angles and range estimates. Though the guns lacked the precision of dedicated AA artillery, they were sufficient to harass enemy aircraft, disrupt bombing runs, and, most importantly, provide a psychological boost to defenders who previously had no credible means to strike back at the sky. The human effort, technological ingenuity, and tactical innovation were just one part of the story. Leadership decisions, enemy adaptation, and the moral and strategic implications of improvising weapons under pressure would soon reveal how critical these early efforts were. Military leadership in 1941 faced a delicate balancing act. Officers at the War Department had to weigh the urgency of anti-aircraft preparedness against competing demands: infantry modernization, naval expansion, and industrial constraints. Some senior commanders doubted the need for AA adaptations, believing that the U.S.'s geographic isolation offered natural protection. Others, however, recognized the lessons of European combat. Air power could strike first, and lethality would outpace any defensive doctrine that ignored it. Leaders like General George C. Marshall advocated for rapid experimentation, empowering engineers and factory managers to test, iterate, and deploy solutions without waiting for bureaucratic approval at every stage. These decisions were critical. By delegating authority to skilled technical personnel, leadership accelerated innovation and ensured that improvised AA systems could move from workshop to field deployment within months rather than years. The looming threat was clear. German Luftwaffe bombers dominated the skies over Europe with devastating efficiency, and Japanese reconnaissance planes prowled the Pacific, scouting harbors and airfields. Both adversaries highlighted weaknesses in American defenses. German aircraft could fly at altitudes and speeds that rendered existing USAA weapons almost useless, while Japanese planes conducted precise low-level attacks that could devastate ports or training camps. Understanding the enemy's tactics influenced every aspect of adaptation. Engineers calculated the likely approach speeds, attack vectors, and bombing altitudes of enemy aircraft. Even minor miscalculations could result in wasted ammunition or, worse, allow an enemy strike to succeed. The presence of a capable adversary created urgency, turning theoretical modifications into life-and-death innovations. The decision to repurpose infantry weapons carried weighty moral and strategic implications. On one hand, adapting existing guns was a pragmatic, cost-effective response to a critical deficiency. On the other, it raised questions about resource allocation. Were soldiers being forced to rely on stopgap measures instead of purpose-built AA artillery? The pressure to innovate under constraint reflected a broader ethical and strategic tension. Protect the nation now with available tools, or wait for superior weapons and risk vulnerability in the interim. Strategically, the improvised guns represented a philosophy that would recur throughout the war. Necessity drives ingenuity. The choice to modify Browning weapons not only addressed an immediate defense need, but also established a pattern of rapid adaptation that would define American military production in the early years of World War II. Together, these angles, human, technological, tactical, leadership, enemy, and moral, set the stage for a decisive moment. Engineers had built workable prototypes, gunners had trained under simulated conditions, and commanders had authorized deployment. But the ultimate test would not be on paper, in factories, or in drills. It would come with the first live engagements, aircraft overhead, tracers streaking through the sky, and the fate of improvised weapons tested under the stress of real combat. The question lingered. Could these adapted Browning machine guns protect American skies when the threat finally arrived? By mid-1941, America's improvised anti-aircraft defenses were moving from prototype to deployment. On the coastal forts of the Atlantic, high-angle Browning M2s were mounted on reinforced pedestals, their barrels polished, recoil systems tightened, and tracer rounds stacked for rapid access. Soldiers drilled relentlessly, learning to coordinate in teams. One spotting the approaching aircraft, another calculating lead angles, a third controlling the gun's traverse and elevation. Every click of gears, every puff of smoke from repeated bursts, was a rehearsal for a confrontation that had not yet arrived, but was inevitable. The first major test came unexpectedly. In early August, reconnaissance reports indicated unidentified aircraft approaching the eastern seaboard. Nervous gunners trained their modified M2s on the horizon. The aircraft never attacked, but the exercise revealed critical insights. Guns could sustain high-angle fire, but recoil still caused minor wobble. Traversing to track fast-moving targets required precise coordination between crew members. Spotters had to refine estimation methods for lead distance, and commanders began considering multiple guns per target to increase hit probability. These lessons were painstaking, but essential. The improvised guns were still unproven in combat, and every flaw had to be identified before enemy fire tested their limits. Meanwhile, on the West Coast and in Hawaii, the stakes were higher. Reports of Japanese reconnaissance flights over Pearl Harbor and along Pacific shipping lanes forced accelerated deployment. Modified Browning guns were rushed to key positions: harbor defenses, airfields, and naval installations. Engineers accompanied soldiers, fine-tuning mounts and sights under the harsh sun, while factory technicians shipped additional weapons to keep up with demand. Even as isolationist sentiment persisted politically, the reality of global conflict forced practical action. Soldiers who had previously fired Browning guns only in training now faced the possibility of using them to defend lives and vital installations against fast-moving enemy aircraft. The human dimension became tangible. Gunners learned to rely on each other under stress, developing silent signals and prearranged firing sequences. Engineers made field modifications on the spot, tightening mounts, adjusting recoil springs, even improvising stabilization platforms from crates and scrap metal. Each successful burst into the sky built confidence. Each missed shot reinforced the need for practice and adjustment. Morale, previously tentative in the face of abstract threats, hardened. Soldiers began to feel that, with ingenuity and persistence, they could meet the enemy on equal terms, even with improvised weapons. These early field tests also exposed limitations. The gun's elevation mechanisms, while improved, could not reach high-altitude bombers effectively. Sustained rapid fire produced barrel overheating and occasional jams. Ammunition supply became a logistical concern. Tracers helped in tracking, but heavy consumption risked depleting stocks before sustained engagement. Commanders documented every issue, sending feedback to factory engineers, ensuring that the next iteration would correct observed failures. In this way, the battlefield itself became a laboratory, merging technical innovation with practical experience. By September 1941, a pattern emerged. Combined deployments of modified Browning M2s along key coastal points, supplemented by smaller caliber M1919s for secondary coverage, provided a credible deterrent against low and medium altitude attacks. Reports noted that aircraft flying within range were more likely to be disrupted or forced to higher altitudes, where they were less accurate and more vulnerable to other defenses. While the guns could not yet repel a sustained, concentrated bombing raid, they represented a meaningful leap in America's defensive capability, a direct product of improvisation, ingenuity, and relentless testing. The tension reached its apex as Pearl Harbor loomed. Crews had practiced tirelessly, installations were reinforced, and the nation's improvised anti-aircraft defenses had never been tested in earnest. Every adjustment, every calculation, and every late-night factory hour converged on the inevitable moment when theory would collide with reality. The question was no longer whether the guns could track fast-moving aircraft, but whether gunners could perform under the stress of real combat, when bullets from the sky could kill instantly and failure meant catastrophic loss. The scene was set across the Atlantic and Pacific. The first true test of America's adapted anti-aircraft weapons approached. The improvised M2s were ready, crews trained, and factories poised to produce replacements. But the coming engagements would determine whether these stopgap solutions could withstand the fire of modern warfare. December 7th, 1941. The sun had barely risen over Pearl Harbor when the first shadows of Japanese aircraft streaked across the Hawaiian sky. Gunners manning the newly adapted Browning M2 anti-aircraft mounts were alert, hearts pounding, fingers gripping triggers. The roar of incoming engines filled the air, a chilling prelude to destruction. These were the first moments when improvised American AA weapons would face the crucible of live combat. As the enemy dive bombers descended, crews rapidly adjusted elevation and traverse, unleashing bursts of tracer rounds into the sky. Coordination was critical. Spotters calculated lead angles, gun teams synchronized fire, and engineers, stationed nearby for field adjustments, monitored barrel overheating and mount stability. The guns rattled under the strain, smoke curling from barrels heated by sustained fire. Early reports later described moments of near panic, as gunners struggled to track multiple targets simultaneously. Yet the M2s fired steadily, demonstrating the potential of these adapted weapons. Several enemy planes were hit, forced to pull away from intended targets, and at least one was observed trailing smoke before disappearing into the distance. The initial success, though partial, was a revelation. These were weapons not designed for anti-aircraft use. Yet in the chaos of real combat, they held their own. Commanders and soldiers alike realized the value of prior months spent testing and modifying mounts, recoil systems, and sighting mechanisms. Each round fired was a testament to the ingenuity of engineers and the determination of crews who had trained relentlessly under winter winds and factory floors far from Hawaii's tropical sun. Across other Pacific installations, similar engagements occurred. Reconnaissance planes probing West Coast harbors were met with concentrated fire from high-angle Browning M2s and M1919s. Although enemy pilots were often able to evade damage at higher altitudes, the psychological effect was undeniable. American gunners could now challenge aerial intrusions effectively. Observers noted that the adapted weapons slowed enemy reconnaissance efforts, disrupted attack patterns, and forced Japanese pilots to fly higher and less accurately, buying crucial seconds for ships, aircraft, and personnel to respond. This baptism by fire also exposed shortcomings. Mounts occasionally failed under continuous fire, barrels overheated, and ammunition expenditure skyrocketed. Crews improvised in real time, switching barrels, repositioning guns, and even reinforcing mounts with whatever materials were at hand. The feedback loop between battlefield experience and technical adaptation accelerated. Engineers revised recoil systems, improved barrel cooling, and strengthened sighting mechanisms. Each engagement became a live field test, providing critical data for the next wave of production and deployment. Within weeks, these lessons informed the first standardized production models of anti-aircraft Browning guns. The M2 variant, now widely recognized as the first effective stopgap AA weapon for the U.S., was integrated into coastal and field defenses across the nation. The combination of rapid prototyping, human ingenuity, and urgent testing transformed a weapon originally designed for infantry into a credible defense against modern aerial threats. By late December 1941, after the shock of Pearl Harbor, the effectiveness of these adapted weapons could no longer be ignored. Reports compiled by the Army and Navy documented multiple enemy aircraft deterred or damaged by improvised M2 deployments. Soldiers gained confidence in their ability to defend strategic points, and engineers refined designs based on real-world combat conditions. The improvisation that began in cold Philadelphia workshops had matured into a practical, field-tested anti-aircraft system capable of contributing to national defense during the earliest months of American engagement in World War II. The decisive moment was clear. Necessity had driven innovation, and innovation had saved lives. Without these adaptations, key installations at Pearl Harbor and across the Pacific might have suffered even greater destruction. With them, gunners and engineers demonstrated that American ingenuity could overcome industrial and doctrinal shortcomings, even in the heat of the first engagements against a skilled and determined enemy. The crucible of December 1941 marked a turning point in U.S. military doctrine. Improvised solutions, born of urgency and technical skill, became standard practice. The success of the adapted Browning M2 guns set a precedent for rapid wartime innovation, proving that even existing infantry weapons could be transformed to meet the demands of modern combat. This moment would influence not only anti-aircraft strategy for the remainder of the war, but also broader approaches to military engineering, adaptation, and production under pressure. The aftermath of these early confrontations would ripple through military strategy, industrial production, and morale, setting the stage for America's next phase in the fight against the Axis powers. The lessons learned in sweat-soaked factories and under tropical skies would shape the development of more sophisticated anti-aircraft artillery and inspire confidence in a nation suddenly at war. The first months following the attacks on Pearl Harbor highlighted the tangible impact of America's improvised anti-aircraft defenses. Across coastal forts, airfields, and naval installations, the modified Browning M2s and adapted 1919s proved more than theoretical solutions. They were life-saving implements in a suddenly urgent war. Reports from the Pacific and Atlantic theaters documented dozens of enemy aircraft deterred, damaged, or forced to alter attack patterns due to the concentrated fire from these weapons. While the guns could not completely prevent strikes, they disrupted enemy operations, giving soldiers, sailors, and civilians critical seconds to respond. The human cost was mitigated in part by these stopgap solutions. Gunners and engineers could see the immediate effect of their labor in smoke-trailing aircraft retreating from their fire. Industrial output ramped up rapidly. Factories that had produced thousands of infantry weapons began churning out modified Browning machine guns at a remarkable pace. Assembly lines adapted to the new specifications. Elevation gears, pedestal mounts, and reinforced barrels were integrated into standardized production. Tracer rounds were packaged alongside each gun, ensuring crews had the tools to effectively track high-speed targets. By mid-1942, hundreds of these adapted weapons had been deployed along the eastern seaboard, Pacific Islands, and key naval bases, establishing a network of defensive firepower that, while improvised, was now cohesive and reliable. Quantitatively, the impact was modest but meaningful. After-action reports indicated that the adapted M2s could effectively engage aircraft flying up to 12,000 feet at low and medium speeds, while lighter M1919s provided secondary coverage for lower altitude threats. Although high-altitude bombers still posed a challenge, the new anti-aircraft network significantly increased defensive capability against reconnaissance missions, strafing runs, and dive-bombing attacks. Commanders emphasized that even a small reduction in enemy accuracy could save ships, airfields, and personnel, turning what had been theoretical preparation into measurable defensive advantage. Beyond battlefield effectiveness, the improvised AA weapons influenced military doctrine. The experience demonstrated the value of rapid adaptation, highlighting how existing weapons could be re-engineered under urgent conditions to meet emergent threats. Officers documented tactics for coordinating multiple guns on single targets, training protocols for gunners, and best practices for field maintenance, guidelines that would inform anti-aircraft operations throughout the war. The Army and Navy both recognized that improvisation could bridge gaps in doctrine and equipment, reinforcing the importance of flexible thinking in wartime strategy. Morale, too, was transformed. Soldiers who had previously felt vulnerable to the speed and lethality of modern aircraft gained confidence in their ability to strike back. Engineers, factory workers, and officers alike took pride in seeing months of labor manifest in practical defense. Letters and diaries from the period reveal a mix of awe and relief. The weapons were far from perfect, yet they were real, functional, and capable of saving lives. The psychological effect of even partially effective AA fire on both defenders and attackers cannot be understated. It signaled that the U.S. was no longer defenseless against aerial assault. Strategically, the improvised weapons bought the United States time. While purpose-built anti-aircraft artillery like the Bofors 40mm and larger caliber AA guns were still in production or in limited supply, the adapted Brownings provided a bridge between vulnerability and preparedness. They allowed the Army to secure key ports, training bases, and logistical hubs, while engineers and designers continued refining new systems. These stopgap solutions were particularly valuable in the early months of 1942, when the Axis powers still held initiative in the Pacific and Europe. Every bullet fired, every mount adjusted in the field, underscored a vital lesson. The United States industrial base, when coupled with ingenuity and urgency, could overcome deficiencies in doctrine and equipment. The improvised anti-aircraft guns, once mere adaptations of infantry weapons, had become symbols of American resilience, innovation, and determination. They were not perfect, but they worked when it mattered most, shaping the course of early U.S. engagement in the war and laying the foundation for future air defense strategy. The success of the improvised Browning anti-aircraft guns reverberated far beyond the immediate battlefields of Pearl Harbor and early Pacific engagements. With prototypes validated in combat, the U.S. Army moved swiftly to scale production. Factories across the country, from Philadelphia to the Midwest, implemented standardized assembly lines for the high-angle M2s and modified M1919s. Engineers refined designs based on field reports. Mounts were strengthened, barrel cooling systems optimized, and sighting mechanisms calibrated for maximum accuracy. By mid-1942, thousands of these adapted weapons were deployed across American territories, coastal forts, and forward bases in the Pacific, creating the first cohesive network of U.S. anti-aircraft firepower in the early war years. Technological refinement continued in parallel. The M2s became increasingly capable of engaging medium-altitude aircraft, while specialized training programs for gunners improved target tracking and firing coordination. Lessons learned from the improvised adaptations directly informed the design of purpose-built AA guns, including the widespread adoption of the Bofors 40mm and the 37mm M1A2. The improvised Brownings, once a temporary solution, have become a proving ground for innovation. Strategies for lead calculation, tracer use, and crew coordination were applied to more advanced weapons systems throughout the war. Strategically, the improvisation demonstrated the potential of American industrial flexibility. By leveraging existing weapons and human ingenuity, the United States gained critical defensive capabilities without waiting years for new designs to enter production. This approach allowed commanders to focus resources on other urgent priorities: naval expansion, aircraft production, and overseas deployment, while ensuring that critical points, including ports, airfields, and training facilities, were not left vulnerable. The precedent was clear. In times of crisis, adaptation could bridge capability gaps, buying time and preserving lives. The human consequences were equally significant. Soldiers trained on improvised AA guns developed skills that extended to more advanced weapons later in the war. Engineers and factory workers who had participated in rapid modification cycles gained invaluable experience in field-driven design, problem-solving under pressure, and iterative production. These lessons, honed under real combat conditions, would be applied to countless other innovations throughout World War II, from tank armor improvements to radar-guided weapon systems. Morale, both on the home front and among deployed troops, benefited immensely. News of effective American anti-aircraft fire reached service members and citizens alike, signaling that the nation could defend itself even before purpose-built defenses arrived. Letters and reports from early 1942 show gunners taking pride in their ability to challenge enemy aircraft, while factory workers felt tangible impact from their labor. The improvised weapons became symbols of resilience and ingenuity, proof that American skill and determination could offset initial technological deficiencies. The broader strategic impact also extended to doctrine and planning. Commanders incorporated lessons from improvised AA deployment into training manuals, defensive layouts, and operational protocols. They recognized that mobility, rapid adaptation, and crew coordination were as vital as the weapon itself. The experience challenged prior assumptions that air defense required wholly new systems. Instead, it highlighted how existing resources, intelligently adapted, could meet emergent threats. By the end of 1942, the improvised Browning AA guns were largely supplemented by purpose-built artillery, but their legacy remained. They had filled a critical gap at a moment of vulnerability, saved lives, and established a model of wartime innovation that would recur throughout the conflict. From Hawaii to the Atlantic coast, the story of these adapted weapons became a testament to human ingenuity under pressure, a bridge between a nation unprepared for aerial warfare and one capable of defending itself against the skies of modern combat. The lessons of these early months would echo throughout the war. Improvised solutions prove that American industrial and intellectual capacity, when harnessed under necessity, could transform deficiency into defense, vulnerability into resilience. The stage was now set for reflection. What these adaptations ultimately meant for warfare, technology, and human ingenuity would become clear only in the years that followed. The story of America's improvised anti-aircraft guns in 1941 to 1942 is more than a tale of machinery and bullets. It is a testament to human ingenuity under pressure. Faced with a world at war, with cities burning abroad and the threat of aerial attack looming over the Pacific and Atlantic, engineers, factory workers, soldiers, and commanders turned limitations into solutions. A weapon designed for infantry, intended to sweep fields and trenches, became a shield against the skies. Necessity had rewritten the rules of innovation. This transformation illustrates the profound interplay between technology and human adaptability. Machines alone could not protect a nation. It was the hands that modified them, the minds that calculated trajectories, and the discipline of gunners under fire that converted potential into effectiveness. The improvised M2s and modified M1919s became living proof that creativity, collaboration, and relentless problem-solving could offset the constraints of time, bureaucracy, and initial unpreparedness. Strategically, these adaptations offered lessons that resonated far beyond the immediate crisis. They demonstrated that defensive gaps could be mitigated with existing resources when guided by expertise and urgency. They shaped doctrine, informed future weapon design, and instilled confidence in soldiers who, facing the unknown, could trust not only their skill but also the ingenuity embedded in the tools they wielded. Yet beyond the technical and strategic, there is a human story. The quiet determination of engineers in snowy factories, the meticulous adjustments of gunners on sun-scorched fields, the coordination and trust required for every burst of fire. Each effort was a thread in a larger tapestry, a nation confronting vulnerability, improvising courage, and learning that innovation is as much about human spirit as it is about hardware. Ultimately, the improvised anti-aircraft guns of 1941 to 1942 symbolize resilience. They remind us that even in moments of unpreparedness, ingenuity and collaboration can create solutions, that necessity can drive brilliance, and that humanity's capacity to adapt under pressure can alter the course of history. From the first test fires in Philadelphia to the skyward bursts at Pearl Harbor, these weapons were more than metal and gunpowder. They were a statement. America could and would defend itself. The legacy of these adaptations extends beyond World War II, echoing as a lesson in creativity, determination, and the enduring power of human innovation in the face of urgent challenges.